Hello everyone. Welcome to the third session on semiconductor fundamentals. In this session, I'm going to discuss on doped semiconductors. In my last session, I in fact presented silicon as an intrinsic semiconductor. By themselves, intrinsic semiconductors are not good conductors nor insulators, and their conduction is largely dependent upon the temperature. We can alter the properties of the material by introducing foreign substances or impurities into the crystal. These impurities are also known as dopants. A crystal with an added dopant is referred to as an extrinsic semiconductor or doped material. The amount of impurity added is generally small, perhaps in the neighborhood of 1 part per million. The dopant may be added through a gaseous diffusion process where the crystal is heated in an oven and the dopant is added in gaseous form. Over a period of time, the impurities will diffuse or seep into the target crystal. An alternate approach is ion implementation. In this method, the impurities are accelerated and quite literally smash into the target, dislodging and replacing some of the original atoms in the crystal. There are in fact two different types of semiconductors possible. One is the N-type material and the other is the P-type material. Here N stands for negative and P stands for positive. N-type material is created by adding pentavalent impurities, that is, a dopant with 5 electrons in its outer shell. Examples include phosphorus, arsenic, and antimony. In contrast, a P-type material is created by adding a trivalent impurity, one with 3 electrons in its outer shell. Possible trivalent impurities include boron, gallium, and indium. Now let us discuss the N-type and P-type semiconductors themselves. Figure here shows a model of a silicon crystal with a pentavalent impurity at its center. Compared to an ordinary silicon atom that would have 4 electrons in its outer shell, the pentavalent impurity creates an extra or donor electron. Thus, the crystal has a net negative charge and is referred to as N-type material. The energy level of the donor electron is just below the bottom of the conduction band as shown in the diagram here. In other words, the difference between the donor level and the bottom of the conduction band is much smaller than the band gap itself. Therefore, it is relatively easy for these donor electrons to jump into the conduction band, becoming free ionized electrons and leaving behind ionized holes. Compared to the undoped intrinsic crystal, the doped extrinsic crystal exhibits a relatively high number of free electrons. As you might surmise, this enhances the conductivity of the material, and the greater the doping level, the greater the enhancement. Earlier, it was mentioned that both electrons and holes can serve as charge carriers. Because the number of free electrons is significantly larger than the number of holes in N-type material, electrons in N-type material are referred to as the majority charge carrier, while holes are referred to as minority charge carriers. The extra electrons add to the number of filled energy states, and being of higher energy than the valence electrons, push the Fermi level to a higher value. Remember, the Fermi level represents the point where 50% of the states would be filled. So, if we add states above this, then the new 50% point must be higher than the former level. This in fact is also illustrated in this diagram here. Note how close the donor level is to the conduction band and that the Fermi level has been pushed up, away from the valence band and closer to the conduction band. This will be of great significance in upcoming discussions on semiconductor devices. Now we move our discussion to the P-type semiconductor. Just like how we doped an N-type semiconductor, in a very similar manner, if we introduce a trivalent impurity, our crystal model now features a hole, a location where an electron is lacking. For this reason, trivalent impurities are sometimes called acceptors. The resulting crystal model is as shown in the diagram here. The resulting situation is essentially the reverse of that of the N-type material. Figure that is shown here shows the energy band diagram for our new P-type material. In this case, the Fermi level has been pushed down closer to the valence band. In p-type material, holes outnumber the free electrons. Consequently, holes are therefore referred to as the majority charge carriers in p-type material, while electrons take on the role of minority charge carriers. As with n-type material, the greater the amount of trivalent impurity added, the greater the overall effect. By itself, a doped crystal can be used to create a resistor. The resistivity of the material is a function of the doping level. By setting the cross-sectional area, length of the doping level, we can create well-defined resistor values. The interesting bits arrive when we combine both N and P-type materials into a single device, as we shall begin to see in the next sessions. Right, so with that, I end this session, and in the next session, we will start our discussion on the junctions. Thank you.